All right, so get this. Today we're going deep, like really deep into the physics that's all around us. The stuff we see every day, but we don't even think about, like, why it happens.
Right, yeah.
Like, why does toast always seem to land butter side down?
Oh, yeah.
Or, like, how do those massive airplanes even stay up in the air? Well, get ready to have your mind blown.
Yeah.
Because we're going to uncover some of those mysteries.
I think a lot of times we take it for granted,
Totally.
We just see it happen and don't even realize there's like science behind it.
Yeah.
Which is really cool when you start to understand those principles.
Like this secret code governing everything.
Yeah, yeah.
So, okay, let's start with something we all experience, like, all the time.
Okay.
Gravity.
Yeah.
That thing that keeps our feet on the ground.
Mm-hmm.
But what exactly is it?
Well, gravity, it's actually just a force of attraction between any two objects that have mass. Now, the Earth is a pretty big object, so it's got a strong, strong gravitational pull.
Right.
That's why we stick to it and things fall down.
Right.
But here's the kicker.
Okay.
The rate that things fall
Yeah.
is the same, regardless of their mass.
So you're telling me that a feather
Yeah.
and a bowling ball,
Yeah.
if you drop them at the same time from the same height,
Exactly.
they would land at the same time?
Same time.
No way.
Yep, that's right.
I don't believe you.
Well, Galileo back in the day, he supposedly proved this
Oh, okay.
by dropping objects with different masses from the Leaning Tower of Pisa.
Oh, wow.
Turns out gravity doesn't play favorites.
Okay.
It pulls everything down at roughly 9.8 meters per second squared.
Okay, so Galileo settled that.
Yeah.
But heavier objects don't fall faster?
Nope.
But that still doesn't explain the buttered toast thing.
Oh.
What's the deal with that? Is there, like, some kind of anti-toast conspiracy?
Well, not quite a conspiracy, but it is physics at play.
Okay.
So think about it. When a piece of toast falls off a table, usually it doesn't fall straight down, right? It rotates.
Okay.
And because of the, height of the table and the size of your average piece of toast, it only has time to rotate like about halfway before it hits the ground.
Okay, I'm following.
So here's the thing. That buttered side, even though it's like a thin layer, it adds a bit of weight to that side of the toast. And because of that uneven weight distribution, as the toast rotates, it's just more likely to land butter side down.
So you're telling me it's not my fault?
Nope.
There's an actual scientific reason why my breakfast ends up on the floor.
It's physics, not personal failings.
Okay.
And speaking of physics, that whole toast debacle brings us to another super important concept.
Okay.
Forces.
Ooh, forces. All right, I like that.
Yeah.
Sounds a little more exciting than just gravity.
Yeah, a bit more action-packed.
Yeah.
So forces, they're literally everywhere.
Go.
Even when things seem perfectly still.
Really?
Think about this. Right now,
you're
probably sitting down.
Yeah, I am.
Feel that chair supporting you.
I do, yeah.
That, my friend, is physics in action.
I don't see the connection here.
Okay, so it's all about forces being in equilibrium. Your body is exerting a downward force on the chair.
Okay, because of gravity.
Exactly, because of gravity.
Okay.
But the chair is pushing back up on you.
Okay.
With an equal and opposite force.
Okay.
Which we call the normal force.
Normal force.
It's this perfect balance,
Yeah.
that keeps you from, like, collapsing onto the floor.
Wow.
It's pretty cool, huh?
So even sitting still, there's like a little physics battle happening.
It's a constant showdown. Oh, my mind is blown. But what happens when those forces, they aren't balanced?
Okay.
Like when you're on a roller coaster.
Right.
And you get that, like, feeling in your stomach.
Exactly. That's all thanks to inertia.
Inertia.
Yeah, so Newton's first law of motion states that an object in motion wants to stay in motion.
Right.
In a straight line at a constant speed.
Okay.
Unless acted on by an external force.
Hold on, inertia. Remind me what that means again.
Oh, yeah.
Like, I vaguely remember from, like, high school physics.
Basically, it's the tendency of an object to resist changes in motion.
Okay.
So when that roller coaster makes a sudden turn, your body it wants to keep going straight.
Right.
So you feel that jolt.
So that's why seatbelts are so important.
Exactly.
They provide that external force
to
keep us from,
Yep, they're lifesavers because they work with physics.
Right.
Not against it.
That makes sense.
But speaking of forces in motion.
I'm curious. Have you ever looked up at a plane flying overhead and wondered,
Oh, yeah.
How something so heavy can just stay up there.
Like, every time I see a plane take off, I'm like, how? How is that possible?
It seems like magic, right?
Yeah.
Well, they're not breaking any rules. Yeah. They're actually using physics.
Right.
Something called Bernoulli's principle.
Bernoulli's principle.
It's all about the relationship between the speed and pressure of fluids.
Oh, yeah.
And in this case, the fluid is air.
Okay.
So imagine you're looking at a cross-section of an airplane wing.
Right.
It's curved on top.
Right.
Flatter on the bottom.
Yeah, I've noticed that.
Okay, so here's the key. As the plane moves forward, air flows over both the top and the bottom of the wing.
Okay.
But because of that curved top surface,
yeah,
the air traveling over the top, it has to travel farther in the same amount of time.
So it's moving faster.
Exactly.
Okay.
And Bernoulli's principle tells us that faster moving air creates lower pressure.
Okay, so faster air, lower pressure. How does that help the plane stay up?
So think of it this way. You've got this low pressure above the wing.
Yeah.
And higher pressure below the wing.
Okay.
That difference in pressure creates an upward force.
Right.
Which we call lift.
Lift, okay.
And that lift force counteracts gravity.
So it's like the air itself is giving the plane a boost.
Exactly. It's this beautiful example of how understanding and manipulating physics can achieve incredible things like flight.
Okay, so it's not magic, it's science.
Exactly.
I'm looking at planes in a whole new way now.
And that's just the beginning. There's so much more to uncover about the physics happening all around us.
All right, stay tuned, everyone, because we are just getting started.
Oh, we've got more mind-blowing physics coming your way.
It's going to change the way you see the world.
For sure.
I'm still thinking about Bernoulli and that whole airplane thing.
It's pretty wild, right?
It really is.
How, physics makes those things possible.
Sure.
So are you ready for more physics mysteries?
Oh, absolutely.
Okay, let's talk about buoyancy.
Buoyancy?
Yeah. You know why some things float and others sink?
I mean, I get that some things are heavier than others, but...
Yeah, it's not just about weight.
Oh, okay.
It's also about density and something called Archimedes' principle.
Archimedes' principle.
Yeah, so this principle states that any object that's, submerged in a fluid, it experiences this upward force called a buoyant force.
Okay.
And that force is equal to the weight of the fluid that the object displaces.
Wait, okay, hold on. Can you, maybe break that down a little?
Sure.
Simpler terms.
So imagine, a rubber ducky floating in a bathtub.
Okay. Yeah.
It's pushing aside or displacing a certain amount of water, right?
Yeah.
Now, if the weight of that displaced water is greater than the weight of the duck itself, the duck floats. But if the duck is denser than the water, meaning it weighs more than the water, it pushes out of the way.
It sinks.
It sinks.
So it's like a little underwater scale.
Exactly.
The object is heavier than the water. It pushes aside. It sinks.
Yep.
And if it's lighter, it floats.
Exactly.
Right. Yeah.
And this principle, it's not just for bathtub tools.
Right.
It explains how ships made of steel can float on the ocean.
Yeah, but how is that possible?
Well, they're designed in a way that displaces a huge amount of water.
Right.
So that creates a really big buoyant force. Enough to support all that weight.
So it's not just about how heavy something is.
Right.
But how much water it pushes aside.
Exactly.
Kind of crazy.
Now, while we're on the topic of water, let's dive into another cool phenomenon. Surface tension.
Surface tension.
Yeah. Have you ever, seen those bugs that walk on water?
Yeah, how do they even do that?
It's pretty remarkable, right? It's all thanks to surface tension.
Right.
So water molecules, they're attracted to each other, creating this, skin on the surface of the water.
Okay.
And that tension is actually strong enough to support, small insects.
So the water molecules are like holding hands.
Yeah, kind of like that.
And those little bugs are just walking across their arms.
That's a great way to think about it.
Wow.
And this also explains why, water droplets form those spherical shapes.
Right.
The molecules are pulling inward, trying to minimize their surface area.
Okay.
And a sphere is the most efficient way to do that.
So there's so much happening at the surface of, a simple puddle.
And it's all governed by those laws of physics.
Okay.
Speaking of water, did you know it also affects the climate?
Oh, yeah. Yeah.
Yeah.
Water is, essential for life.
Right.
But how does it affect the climate?
So water has this amazing ability
Right.
to absorb and release heat. It has what we call a high specific heat capacity.
Okay.
Which basically means it takes a lot of energy
Yeah.
to raise its temperature.
Right.
This property helps keep the Earth's temperature relatively stable, preventing those big swings between hot and cold.
So that's why coastal areas tend to have milder climates than inland areas.
Exactly.
Because they're near those huge bodies of water.
Yeah. The oceans act like these giant heat sinks. They absorb heat during the day and then release it slowly at night.
So they're like Earth's built-in temperature control system.
It really is quite amazing, right?
It is.
Now let's shift gears a bit and talk about light.
Light.
Yeah, that thing that lets us see.
Well, yeah, I mean, isn't that just light?
There's actually a lot more to it.
Really?
That meets the eye.
Okay.
Light is actually a form of electromagnetic radiation that travels in waves. And these waves can do some pretty cool things.
Like what?
Well, for instance, have you ever wondered why the sky is blue?
I mean, I guess I've always just kind of accepted it.
Yeah, most people do.
That the sky is blue.
But there's a reason for it.
Okay.
It's because of a phenomenon called Rayleigh scattering.
Rayleigh scattering.
Yeah, so when sunlight enters the Earth's atmosphere, it collides with these tiny air molecules. And these molecules scatter the shorter wavelengths of light, which happen to be blue and violet more effectively than the longer wavelengths.
So it's like the air is filtering out.
Yeah, kind of like that.
All the other colors.
Exactly.
And just leaving blue.
That's why we see a blue sky.
Okay.
And then as the sun sets, the light has to travel through more of the atmosphere, scattering away even more of the blue light.
Because that's why we get those
exactly
beautiful red and orange hues.
during sunset.
So sunsets are basically physics in action.
It's all about how light interacts
with the world around us.
I'm literally seeing the world in a whole new light.
I love it.
Yeah.
And speaking of light behaving in interesting ways, have you ever heard of refraction?
Refraction.
It's like the bending of light.
Yeah.
As it passes from one medium to another,
Okay.
like from air to water.
Okay.
Have you ever noticed how a straw in a glass of water looks broken?
Yeah, it's kind of freaky.
It is, right.
Yeah.
But that's refraction.
Okay.
So the light from the straw travels from the water to the air, and it bends as it crosses that boundary, making the straw appear, displaced.
Like it's broken.
Exactly.
So it's not actually broken.
No.
It's just an illusion.
It's an optical illusion created by the bending of light.
My brain feels a bit bendy now.
I know. It's a lot to process.
Yeah.
And this is what makes lenses work.
Oh.
In eyeglasses, cameras, telescopes.
So every time I wear my glasses, you're harnessing the power of physics.
Wow, that's pretty amazing.
It's pretty cool, right?
We went from floating ducks to the blue sky to bending light.
It's all connected.
It really is incredible how much physics is around us all the time.
Right.
This deep dive has been amazing.
I'm glad you're enjoying it.
I am.
There's still more to uncover, though.
Oh, there is?
But we'll have to save that for the final part
of
our deep dive.
All right. Well, don't go anywhere, listeners.
Yeah, we've got even more mind-blowing physics coming your way.
It's going to change the way you see the world.
It really will.
Okay, so are you ready to wrap up our physics deep dive?
Oh, absolutely. There's still so much to talk about.
Okay, well, let's hear it.
All right, let's talk about sound.
Sound. Yeah.
Yeah, it's something we experience all the time.
Yeah, constantly.
But we rarely really, think about it.
Right.
But sound it's actually a physical phenomenon.
Yeah.
A wave of vibrations traveling through a medium like air or water.
So when I'm listening to music, it's because those sound waves.
Exactly.
They're traveling through the air, hitting my eardrums and making them vibrate.
Exactly. And then those vibrations are transmitted to your brain, which then interprets them as sound.
It's pretty amazing when you think about it.
It really is.
But, okay, what about different qualities of sound?
About?
Why does a trumpet sound different from a violin?
Yeah, even when they're playing the same note, it's all about the shape of the sound wave.
Okay.
Different instruments, they produce different wave shapes. And our ears, they perceive that as different timbres or tone qualities.
So it's each instrument has its own, sound fingerprint.
Yeah, you could say that.
Okay, and here's another thing I've always wondered about.
Yeah.
The speed of sound.
Okay.
Doesn't it travel faster through water than air?
Yes, exactly.
Why is that?
So the density of water, it allows sound waves to travel much farther with less energy loss.
So it's like an underwater highway for sound.
You got it.
I've also noticed that, like, the sound of a siren changes as an ambulance passes by.
Oh, yeah, that's a classic example of the Doppler effect.
The Doppler effect.
Yeah, so as the ambulance approaches, the sound waves are compressed, higher frequency, which we hear as a higher pitch.
Right, right.
Then as it moves away, the waves stretch out, lower frequency, lower pitch.
So it's not the siren actually changing.
Right.
It's our perception of the sound that's changing.
Exactly.
Because of the motion.
So the Doppler effect explains, like, sirens, but it's also used in astronomy.
Yeah, it's used to study the motion of stars and galaxies.
That's pretty amazing.
Isn't it?
That the same physics applies to, like, everyday stuff.
Right.
And these huge, distant objects in space.
The laws of physics are universal.
Wow. I've got to say, this deep dive has been incredible.
Oh, I'm glad you enjoyed it. I've learned so much about, like, gravity and forces, light and sound.
Yeah, it's all connected, right?
Yeah, and I'm definitely seeing the world in a whole new way now.
That's the beauty of understanding science.
Like, I don't know.
Yeah.
A whole new perspective.
It really is.
So next time I drop a piece of toast or see a plane fly overhead, I'm going to be thinking about all this amazing physics.
I hope so.
Well, thanks for taking us on this deep dive.
The pleasure was mine.
It's been an amazing journey of discovery.
And remember, never stop questioning the world around you.
That's great advice.
Until next time.
See you later.